one of the most famous proofs in geometry is Euclid's proof of the Pythagorean theorem. And he proves literally that a squared, this square, plus b squared is equal to this. The squares actually have the same area, and I'll show you how he does that. The general idea is to draw this altitude here and to prove that this square here is the same area as that rectangle, and this square here is the same area as that rectangle, and then the sum of the two squares is the sum of the two rectangles, which is c squared. And the way he does that is by introducing two line segments here, one here and one here. This is the start. Now these two new triangles, this one and this one, those triangles are congruent because this side is congruent to this side. They're both part of the same square. And also this side is congruent to this side. They're part of this big square on the bottom. Then you have a right angle here and a right angle here because those are squares. And this angle in the middle, whatever it is, that means this obtuse angle is the right angle plus that acute angle. And this obtuse angle is also the right angle plus the acute angle. So those two triangles are congruent. And if they're congruent, they have the same area. But this triangle here facing this way has the same area as this square because they have the same base and their heights are the same because the height of the triangle is right here, and that's also the height of the square. So and this other triangle, the base is kind of this way, which is the same as the base of this rectangle, and the height of the triangle is kind of here, but it's the same as this. So the same base and same height. So that means that this square has the same area as this. The square is twice this triangle, and this rectangle is twice the other triangle, but the triangles are congruent. Now you could actually do the same thing on the other side. I would draw this line to create one triangle, and I would draw actually that's not it. It would be this line to create one triangle, and this line to create the other triangle. And by the same reason as before, this side is congruent to this side. They're part of the same square, whereas this big bottom side is congruent to this side because they're part of the same square. So this triangle here has the same area as this red square, whereas this triangle here has the same base and height as this red rectangle. So the red square, the triangles are congruent, so the square and the rectangle have the same area. And when you put together the red and yellow rectangle, it becomes the large C squared. To create an angle bisector, you make a circle, creates this isosceles triangle. Then you make an equilateral triangle on this line segment connecting these two. And when you connect them, what you'll end up with, by side, 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 you have these two obtuse triangles are congruent, therefore their corresponding angles are congruent, and that's how you make an angle bisector. To trisect a line segment, or to cut a line segment into any number of equal pieces, you make a line segment any length you want, in any direction you want. And now just copy that line segment 2 more times, or 3 more times, whatever you need. When you connect this to this, you make a big triangle, and then you make 2 parallel lines. And this line segment here is cut into 3 equal pieces. But this guy is also, because this triangle, all these triangles are similar, they all share this angle, and these are all corresponding angles because of the parallel lines. So this triangle here is twice as big as this triangle here. This side is twice as big as that side. So that makes this side twice as big as this side, makes this equal. And the same thing over here. This triangle is triple this one, so that means that this side is triple that side, so that means this is equal also. So that's how you can trisect a line segment. If you have a triangle and you extend one of the sides, and it makes, let's just say this is 80 degrees and this is 40 degrees. This angle here will be 120. It's the sum. They say the exterior angle is the sum of the two remote interior angles. If you didn't know that rule, you could work it out pretty easily. 80 plus 40 is 120. 180 minus 120 is 60. That's this guy. And 180 minus 60, because they're supplementary, is 120. So the exterior angle is the sum of the two remote interior angles. If you make a semicircle and you make a triangle, this triangle will always be a right triangle. And the reason why that is, if I take this center of the circle here and connect it, I've created a bunch of isosceles triangles. So if I call this, I'm just going to call it angle 1, that's also angle 1. If I call this angle 2, that's also angle 2. But if you look at the big triangle, this angle is angle 1 plus angle 2. And the three angles of a triangle add up to 180, so angle 1, that's this, plus angle 1 plus angle 2, that's this, plus angle 2 has to equal 180 degrees. That means that 2 angle 1s plus 2 angle 2s equals 180 degrees, or 1 angle 1 plus 1 angle 2 has to equal 90. So this will always be a right angle. If you have a right triangle and you have the midpoints of the hypotenuse and you connect it to make a median, this length will always equal this length because it goes to the midpoint. But what's also true is that this length will also be equal to that. And the easy reason why that is that if you drew a semicircle around the right angle, just like every semicircle has a right triangle in it, if you have a right triangle, you can make a semicircle around it, and then all three of these would be radii of the right triangle. So in a specific case, here's a 5, 12, 13 triangle. If I make the median, this will be 6.5, this will be 6.5, this will be 6.5. Trisecting an angle with a compass and straight edge is not possible. But there's this way to cheat with it, Archimedes method. Here's the angle I want to trisect. I extend to make a diameter. I extend this line and I make a circle here, so this line becomes diameter, and I continue it. And the trick is, somewhere around here, there's a point that if I connect this point all the way to this one, if I can do it so that this line segment is also equal to this radius of this circle, the angle will be trisected, and let's see why that is. If I draw on this line, that will be a radius. So we have a lot of equivalent lines here, and we have two isosceles triangles. So this angle here is equal to, it's an exterior angle to this large triangle. So it's equal to, I'll just call this angle 1. I'll call this one up here angle 2. So the red is equal to angle 1 plus angle 2. But there's also a 2 here because this is an isosceles triangle, and this 2 is an exterior angle to this one, but since this is an isosceles, so it's equal to 1 plus this other angle, but that angle is 1 also because it's an isosceles triangle, so angle 2 can be replaced with angle 1 plus angle 1. In other words, this angle here is equal to 3 times angle 1, so angle 1 is 1/3 of the red angle, and the angle's been trisected by Archimedes method. Another way to trisect an angle, a configuration for it, is here's a right triangle, and my goal is to trisect that angle. And if we make this parallel line to this base, if I could find a point, listen to this carefully, a point somewhere over here, so that when I connect these together, if it's true that this line segment, not the whole line segment, just from here to here, is double this, then look what happens. This is a right triangle. If I can get this to happen, here's the midpoints of that side, so this would be x and x. Connect this. There's a rule that the median drawn to the hypotenuse is also equal to half the hypotenuse. So what I have here is a lot of isosceles triangles. That line gets in the way, so let me get rid of it. So I actually don't need this right now either. Okay, so let's see what we have going on here. This angle here, I'll call angle 1, is equal to this angle here because of alternate interior angles. So that makes this angle 1 also because it's an isosceles triangle. They're both x. Let's call this angle 2. This is also angle 2 because it's an isosceles triangle. But angle 2 is the exterior angle, so it's angle 1 plus angle 1. So this is angle 1 plus angle 1. So that means that this whole thing is 3 angle 1s, so it's triple, which means angle 1 is 1/3, and that's Hippocrates' way of, if we could find this point so that this line segment is double this line segment, that will happen. There is a curve called the conchoid of Nicomedes, and the way it works is you have a line called the directrix, a point called the pole, and this other line segment called the distance. And what you do is you go towards any point on, from the pole to any point on the directrix, and then you continue this amount in a straight line. Get a point on the conchoid. If I go straight up, I have to go up this amount. I get a point so a little higher. And if I go at kind of a angle like that, the point ends up kind of low, kind of over here. And when I put them all together, I get this kind of shape. If instead of going forward, when I hit the line, instead of going forward this amount, I go backwards that amount, I end up over here. And there's another curve that ends up happening that looks something like that, another branch. But really it's this top branch. That's the one that's important to us. If I have a line segment, if I have an angle that I want to trisect using Hippocrates' method, the way I find that special point is by making a conchoid. If this is the pole and this is the directrix, and I make as my distance double whatever this is. So I end up with a curve kind of like this. Now at any point, if I connect the pole to any points on the conchoid, this distance will be double that distance. Or if I go like that, then this distance, because that's what the conchoid is. Every point is, in this case, because I'm making my conchoid with a special distance of double this. So if I go towards the directrix and keep going till I hit the conchoid, or if I go this distance, I get to a point on the conchoid. But the most important point is right here, because this will also be 2x. And this is the configuration from before, this one. So if I have the ability to make a conchoid, I can use it to locate this point, and then I will have trisected the angle with the conchoid. The spiral of Archimedes is a curve that you get by, here's a circle, start over here, and then as this line kind of rotates, this point over here moves outward, so that by the time the line rotates all the way around, the point's back over here. So, for instance, when the line has made it 1/4 of the way, this point will be 1/4 of the way. When it's halfway, it will be halfway. When it's 3/4 of the way, it will be 3/4. And you end up with a curve that looks something like that. If you want to trisect an angle, suppose it's this one, with the spiral of Archimedes, what you do is you find the intersection of, this one's always going to be horizontal. Here's the other side of the angle. So I find this point, intersection of the spiral with the other side, the non-horizontal side of the angle. I trisect this line segment, which is something you can do, and then I make another circle, and where that circle intersects the spiral, that's going to be the trisected angle. And the reason why that is that if this line segment here, if this line segment is 1/3 of that line segment, this angle will be 1/3 of this angle because it's sort of proportional. And that's how you can trisect an angle with the spiral of Archimedes.